Thank you, Vanessa. I'd like to talk to you about our ConCert framework, which is a framework in the Coq proof assistant for the verification of smart contracts. So first of all, I'd like to tell you a bit about the COBRA Center where this work takes place. So COBRA stands for Concordium Blockchain Research Center. So this is a big research center at Aarhus University in Denmark, which is sponsored by the Concordium Foundation. So last year we organized TVBC in Aarhus, and this was a big success. And now we're very happy to do that. Vanessa has taken the role to organize this in Spain. Unfortunately, we could not do this in Spain, but we're very happy with the collaboration with Vanessa in Spain, and we're happy that so many people actually showed up virtually. About the Concordium company, the Concordium company is developing a privacy-centric, public permissionless blockchain built for businesses. And there's a strong emphasis on science and software quality. So there's a lot of collaboration between the university and the company, and we have weekly lunch meetings together and a lot of communication going on between us. So I'd like to put up the pictures of Danil and Jakob. So Danil is a postdoc in my group, and Jakob is a PhD student in my group, and they've been very important in the development of this ConCert framework. There are 2 publications connected to this work. So what's the problem I'd like to talk about? So smart contracts, they operate in a unique adversarial environment. The contracts guard millions of euros behind a few lines of code. A lot of people know about the DAO. This is basically a distributed funding agency that, due to a small bug, or some would say a feature in the contract, someone took out about 50 million euros. Recently, we had a very similar attack on a distributed exchange called dForce, and as you can see the picture here on my screen, they lost 25 million euros in a very short time. And this was again a very similar attack to the one of the DAO. What is very striking on the blockchain, as you probably know, is that after deployment it's very hard or impossible to change. So this is the Code's law. Now we want to model these smart contracts. That's quite difficult because smart contracts, they interact in very complex ways. So it's not enough just to reason about the contracts in isolation. For example, if you consider a crowdfunding contract, this can always try to pay back the funders. So we really need to be careful when reasoning about these blockchains, and that's what makes it so hard also to do it informally. So it's not that these people were particularly dumb. It's a very hard problem to do this right. So now, fortunately, we have a long tradition in mathematics and somewhat shorter in proving software to be correct. So if you want to reason about imperative programs, that's difficult. But reasoning about functional programs, it's much easier because functional programs are just mathematical functions. I'm lying a little bit here, but people that know what I'm talking about will know what I mean. What's happening in these computer proof assistants is it's an interaction, a game if you want, between the human and the computer. So the human constructs the proof, and the computer checks it, and the computer will tell you, well, I can now progress the proof a little bit, but I still need some help in figuring out this aspect. So it's really a dialogue between you and the computer is really helpful to make sure that all the details are actually checked. We're using, and lots of people with us, the Coq proof assistant, which is a foundational proof assistant, which means that it reduces a proof all the way to the actions of mathematics. So if you have checked your proof in this proof assistant, you can be very sure that the proof is actually correct and that you haven't missed any cases. Of course, we're not the first one to suggest this. And quite a few people in the formal methods community have looked at reasoning about smart contracts. However, the modeling something like the DAO in a foundational way is still very hard, and we're the first to actually do this. So most of the previous work, this has focused on local functional correctness. This is, for instance, done by deductive verifiers and static analysis. That's already very useful, of course, because if there's if you make a mistake in your addition or multiplication, you can see that you can also lose a lot of money. And this may seem trivial, but I mean, you could have underflows or overflows. So it's very important also to have this local functional correctness. Some models are limited to some tools only, or formalizations only model very limited parts of the surrounding environment. There's the key work on simplicity was one of the first works on verifying smart contracts inside the Coq proof assistant. And the Scylla also contributed a lot, and Michaud Coq of the Michelson language of the Tezos company. So they're not really in reasoning about the interaction of contracts. Now, fortunately, the Coq proof assistant allows us to model all of mathematics. So it has a sufficiently advanced language for the concrete contracts, the execution layer, and we can use all of mathematics to reason about this. So if we can prove something about these contracts on paper, well, the first thing is we would have an informal argument that it's correct. Then we could try to make a mathematical proof, but we could actually completely capture this mathematical proof in our proof assistant. So we can do all of this in the Coq proof assistant. Moreover, the Coq proof assistant has a built-in functional language. Recall that what I said in the beginning, a computer program in a functional language is just a mathematical function, so we can reason about them as functions. And all of this is captured very nicely in the Coq proof assistant. So what is the execution layer? So as you can see in the example here, we have a user A that calls a contract X, and then the contract X sends a message or some money to user B, or to user D, and it calls a new contract Y. And Y again sends a message to user C. Now we have this whole tree, and then the question is, how do we actually handle these calls, these messages? There are at least two ways to do this, and both are actually reasonable. The Ethereum is using the depth-first search, so actually you can see that the message from contract Y to user C is done first before message 5. Whereas in the breadth-first search, which is used in Tezos and Silica, this goes in the other way around. You can, the red and the blue parts, the ones are different. So the execution layer takes care of the state updates and importantly also about the ordering of messages. So this will be very important for reasoning. Now we model the execution layer. So there, as I said, so there are multiple reasonable ways to schedule these calls. And some properties may hold in one order and not in the other. One example is the deforce attack. This is much more difficult in one order than in the other. But what we do in our work is we leave the execution layer completely general, and then we can later instantiate it if we want to reason about things that are particular for one execution layer. So we have no restrictions on the order, and the other details are also unspecified. So in this way, we can capture a number of execution layers, and including the one of the Concordium company, as well as the ones that I mentioned before. So this is just to give you an idea of how we actually model the contracts. And here you can see that if you're used to programming in a functional language, then this is something you'd be quite familiar with. So a contract has two functions, init and receive. And you can see that, so in it takes a chain, a contract call context, and then may return a state, and similarly for the receive function. I just mostly wanted to give you this as an illustration to see how it's actually modeled. So the chain takes information about the world, about the contracts, the contract's view of the world, and the contract call context contains all the information about the call. So this, I hope this gives you some idea of how we do our modeling. What is important is that the contracts actually interact explicitly with the execution layer. So the calls, the transfers, and the deployments, they're all communicated explicitly as a data type. The action body you can see at the end of the receive function. So the implementations, they must exhibit a trace that ends in the current state. And we give, as I said, we give two implementations, a depth first and a breadth first implementation. And both of these actually, the nice thing, as I said, so functions in Coq are computer programs. So these two implementations we can actually run inside the proof assistant, and this will also help us to actually do the proofs and also to play with the proof. So I'll say a bit more at the end. We can also do property-based testing about these proofs. So the DAO contract is somewhat longer, and it contains a number of things that are not so relevant for the actual attack. So we choose to take basically the core of the DAO. This is called the Congress, and this is a standard educational contract on the Ethereum blockchain, and we re-implemented this inside the functional language inside the Coq system. So what it does, it allows members to vote on proposals, and then these proposals contain a number of actions, and there's a complex dynamic and dynamic interaction between them, because once it's a proposal's carried out, it can make a call, and one of the calls it could, one of the actions it could do is call back to the original contract, and this is precisely what happens with the re-entrancy bug in the DAO. The logic about this Congress is fairly short. It's only 200 lines of code, so that's nice because that makes it very manageable. Now, what is the Congress? As you can see, again, I give you some illustration of how this actually looks in the proof assistant. So what kind of messages can be sent? Well, we can transfer ownership, we can change the rules, we can add a member, we can remove a member, create a proposal, vote for a proposal, vote against a proposal, retract a proposal, finish a proposal. So this is just to give you an illustration of what the Congress actually looks like. But you would imagine that if you think about what an actual Congress does, it passes new laws, and it makes proposals for new laws, and then this is a way of simulating what a Congress does on a blockchain. Now, what many of these formal method tools that came up as a reaction to the DAO hack, so a quick analysis after the DAO hack was that re-entrancy was a problem, and this is something that one can test statically. So there are quite a few static analysis tools that allow you to look for re-entrancy. The problem is that the Congress actually needs re-entrancy to really work. And also another thing, of course, is once you know that a certain problem exists, it's easier to look for it. So our starting point was different. What we tried to do was to write the contract, then write a reasonable specification for it and see whether we would find the bug in this way. So we did a partial specification. We developed a list of 10 different properties just to get to state the behavior we wanted of the Congress. And one of the things that one comes up with is that and this is something that one of Jakob's insights, the number of transactions that are sent out is less than the number of transactions that creates proposal message. So this is something that you want to prove as an invariant. And once you start proving this, you see that this is not provable, and this also shows you where the possible attack is. Moreover, so we made both a vulnerable Congress that still has the bug and a safe Congress that actually has this wanted property, this black box specification. And moreover, we proved that this not only holds for the depth first search from Ethereum, but also for any other execution layer. I mean, any other execution layer that fits our specification. So it's actually more general than just for the Ethereum blockchain. So this is a conclusion of the first part of the talk. So we give a formalization of execution layers in Coq. And it's very important to emphasize that contracts don't live in isolation. We prove that the Congress is safe against DAO-style attacks. And we do this by proving natural properties of the Congress. So it's, we proved it. We do this by proving natural properties about the Congress. So now there are a number of questions that come up. One thing that was important in the original attack was the amount of gas or energy that's needed. So reasoning about resources. Reasoning about resources is harder. So I'll address this. I'll show how our framework actually handles this. Could potentially handle this reasoning about resources. So I'll show how we address that problem, how we plan to address that problem. So now we have some functional language in the Coq proof assistant, but now we want to be sure that this actually corresponds to the smart contract that's actually running on chain. So there's a question on how we do this. And we'll make a connection to the Concordium midlang language, which is very close to Elm, the Elm functional language. Another big question is, we made these verified execution layers. And again, how does this correspond to things on chain? There is an extraction functionality inside the Coq proof assistant that would potentially allow us to, that allows us to translate programs in the Coq proof assistant to both Haskell and OCaml. So we could potentially run this execution layer on top of the actual implementation. Our modeling, of course, doesn't use the most advanced data types. So it's only a mathematical model of the actual code. So one thing we would like to do in the future is actually optimize this execution layer to be much more efficient. And then we could potentially extract this to the running code. So as I said, we cannot currently reason about resources. To be able to do this, to reason about the meta theory, we want to use what is called a deep embedding in the proof assistant. People that are familiar with the field will know the difference between deep and shallow embeddings. For the non-experts, you could think about Magritte's famous painting, Ceci pas un pipe. And the message of the painting is, well, this is not actually a pipe, it's a picture of a pipe. We have something very similar in logic. So in the shallow embedding, the functions in our smart contract language are modeled as mathematical functions. But that means we cannot reason about the code of the function. So that what happening in the deep embedding is that one actually has the code of the program in hand, and this is very convenient for the meta theory. And if you have the code of the program in hand, you can also reason about the execution of the function and for example, bound it by the amount of gas that's sent to that particular function. We have not done that last part, but we now have the possibility to actually do so. What is new in this technique? So usually one chooses either the deep embedding or the shallow embedding for one particular problem. What we've done here is to make a very tight combination between the deep and shallow embeddings. Now the question is, what is the smart contract language we're actually reasoning about? And what we've done here is to abstract from a number of functional smart contract languages. And we've taken what we call lambda smart, which is an explicitly typed system F with abstract data types and structural recursion. This is more or less the core language of the Concordium blockchain, which is called Redlang, or it's a pure subset of an ML-like functional language. So this is really a very standard language, and this can also be translated to, for instance, the Tezos or the Tezos or the June blockchains. So before I come to how we combine the deep and the shallow embedding, let me tell you a little bit about the MetaCoq project. So what we'd like is, by using this proof assistant, to know that things are absolutely correct. Now, Coq is about 30 years old, and occasionally one finds a logical correctness bug, and these are extremely subtle. And it's actually very unlikely that these are actually used if you actually deduce your proof. But still, people want the Coq developers want to have an even higher quality of their tool, and this is why they're developing the MetaCoq project. So we prove Coq correct in itself, and if you have a logical background, then you can see that there's a Gödel problem coming up here. But this can actually be circumvented in this case, but it's a completely different story. But in particular, there's a formalization of Coq's evaluation, and this is very convenient because that's now what we're going to compare with. So we have our evaluation of the smart contract language, and we're going to prove inside the Coq system that the evaluation is precisely the same thing as the evaluation of Coq. So then we're absolutely certain that the two models are the same. One other thing that the MetaCoq project allows us is to have certified compilers. And one nice consequence of this is when one writes an interpreter inside this framework, one can easily automatically get a compiler out of this. So this is also something that we expect to get some mileage out, because once we have defined an interpreter, we can actually run it very efficiently inside this framework. So here's the big picture. What we do is we start from the left. We have our AST from our smart contract language, our abstract syntax tree. Then we basically copy this by a script one-to-one into the deep embedding. So then we have an encoding of this AST inside the system. Then we translate it, but there are a number of transformations that are needed in this translation. So we translate, what it does is it takes system F plus inductives and it translates it into the meta theory of Coq, which, as I said, is very close, but there's still quite a few non-trivial transformations that need to be made. What we do, and that's the square on the left, this is checked to be absolutely correct. So we have a soundness theorem. If the smart contract actually terminates, then the outcome guarantees with the certified evaluation in Coq. So there's a very high a level of guarantee that everything is completely correct. But then we want to go further, because then we have this functional program, or the encoding of this functional program inside the Coq system. But we also want to run these things, and in particular we want to hook it up with the execution framework that I showed you in the first part of the talk. So then we connect it basically by interpreting this code into a functional language, into the shallow embedding. So then we get regular Coq programs, and we at this level we can also already very conveniently prove functional correctness properties. But moreover, we have connected it up with the execution framework, so we can now reason about very complex smart contracts like the custom coins, Uniswap, the DAO, all these things we have, or the Congress, all these things we actually have done in this framework. So there's a lot we can already do in this very big square. We have everything verified. So we have everything from the code of the smart contract language to the execution framework that has been verified in the Coq system. So this was the status when we submitted the paper to TBBC, but we made a bit of progress since then. So what we did was this is an abstract that was accepted for the Coq workshop. This was together with a master student that also joined. And there what we did was to combine three things in our ConCert framework. So we made three additions. One is we started to look at the open vote network, because it's a very interesting way of doing voting on chain, but for a somewhat limited group. There are issues with voting on a nationwide scale, but this can be done for limited groups. This is sometimes called boardroom voting. We proved functional correctness of the cryptographic primitives, and this includes quite a few key building blocks for zero knowledge proofs, like Sigma protocols, the OR construction, and so on. So this is already this demonstration that those kind of that kind of mathematics can actually be developed quite nicely inside this framework. Then there's work on property-based testing. That's a standard semi-automatic way of finding bugs in functional programs, so-called the quick check. That's a program for Haskell. And there's a version also within inside the Coq proof assistant, which actually allows to have a very nice combination of first checking that things, or testing that a certain property holds, and then one can later go further and actually proving that it holds. The nice thing is that this is semi-automatic, so it's possible to do by less expert people, and it will also be cheaper because it's faster. And this can capture both functional and temporal properties. With a bit of guidance, this semi-automated testing finds the DAO bug and also the D-Force Uniswap vulnerability. So that's also a new contribution. Then what I showed you here is that what we could do before is go from the smart contract language and go inside the proof assistant. But of course, once we've done all the work inside the proof assistant, we want to go back to the actual smart contract and make sure that if we write a new smart contract inside the proof assistant, we can also run it on chain. So this is done by verified erasure. So we take the program inside the proof assistant, and then we translate it either to the midlang language of Concordium or to liquidity, which is used on Tezos and Dune. And it can also do other functional languages. or it should be able to do that by doing standard modifications, just like standard Coq can extract to both Haskell and OCaml. And what we've shown there is to do crowdfunding and also a simple financial domain-specific language. And this is like the Marlow language that's running on the Cardano blockchain. And there are other financial domain-specific languages that are also in use. So this shows that's possible to also capture this in our framework. But it's important to note that this erasure is quite a bit more difficult than the standard erasure from Coq to either Haskell or OCaml, because in this case, in that case, both of these languages, they have escape hatches. So you can write a term that's not well typed. That's not possible in smart contract languages because then instead of getting a compiler error if something could go wrong, you would have a much bigger problem on chain. So that's not possible, and we need to actually take a different route. But this is something that that we've managed to do. So just to sum up, I told you about the deep and shallow embeddings in one framework. We get the soundness through the formalization in the proof assistant. We can verify Redlang code and parts of the standard library and some simple contracts. We have example properties of a crowdfunding contract. We have testing. We have a voting network. We have custom coins. We have the Congress, of course. Tight integration with the execution model, and then extraction or erasure to functional smart contract languages. And all of this code is available on GitHub at our Cobra website. Thank you for your attention.